Guys, today we're starting a new chapter, stresses in beams. So, stresses in beams. And you already know what is a beam, no? You already know what is a beam. So how is it different from a body under compression and body under tension? And you know how is it different from cylinders? Okay? So what is a beam basically? I think we have seen SFD BMD, shear force and bending moment diagrams in beams. So beam is basically a member which takes lateral load. So usually we actually write it like this. It's a beam. It's a beam, maybe a simply supported beam or something. When you apply a UDL or something, or even a moment at the ends like this, the beam bends like this. Okay. Now, if you observe the beam, and I'm trying to zoom this part. Okay, I'm trying to zoom this part here. Okay. So initially before, I mean, you can say 1 is actually before bending, and 2 is after bending. Before bending, it was like this. Before bending, it was like this. It was like this. And after bending, it is like this. Okay. Now you can see that if this length is actually equal to, say, around 100 mm, and you feel that it would be 100 mm at the bottom also. Okay. Now after bending, what do you think would be the length here, from here to here? From here to here, now what do you feel the length it would be? Now would it be more than 100 mm or less than 100 mm? Less than 100 mm. Say around 98 mm. 98 mm. Now what do you think would be the length at the bottom fiber? Increase how much? If it is 98 above, it will be 102 by common sense. Okay, 102. Now, if you see a fiber below it here, will it have now how much it would be? Will it be 98.1 or 98.2 or something? Or will it be less than 98? Guys, respond. Now will the length of the fiber be above 98 or less than 98? I don't know, simply you're saying it is 98, it is 102. So now this fiber below this, will it have a length above 98 or below 98? Above 98, so maybe around 98.2 or something. And a fiber below again will be 98.4, something like this. And here it will be like 101.8 something and 108.2 like this, 101. At some point it will be 101, and at some point it will be how much? 100. At some point it will be 100. Okay. So you understand that when you try to bend a part like this, some fibers would actually get shortened. So when you actually try to shorten something, it is as good as trying to apply a compressive load. If I apply a compressive load here, now what would happen to the fibers here? All these fibers here, they would get compressed. So this is like these fibers are getting what? Compressed. So these fibers are getting compressed. These fibers are getting expanded. Now, there is one fiber at the center, usually at the center it would be. Suppose if it is a rectangle, it would be at the center. If it's a triangle, then it could be somewhere at the, now what do you call this as? Centroid. Okay, centroid somewhere. So somewhere, you can actually determine where it is. If it is actually a rectangular section, it would be exactly at the geometrical center here. So all the fibers that are starting from this point will be the fibers which are neither in tension nor under compression. So there's a fiber at this point which is not stressed at all. Guys, this is not under compressive stress, this is not under the tensile stress, because its length has not changed. The length of this is equal to 100 mm. Original length was 100 mm, now this length is 100 mm. Okay, now you know that we have an equation dl is equal to, so please can you tell me what is the equation that you use to find change in length when you apply a load P, original length L, area is A, Young's modulus is E. Now what is the formula? PL by AE. So PL by AE. Now this P by A can be written as sigma and this can be written like this. So where you can introduce this as deformed length. If you suppose if you are trying to induce some deformation, what is the stress induced will be given by this equation. Okay. Now more the deformation, more the change in length. So that means this original length is the same, Young's modulus is same, this is constant. So it will not vary. More the deformation, more the stress. So that means if you deform the top layer more, so that means its stress will be more. Suppose if I am trying to plot a graph here, now it is a very unique graph. Now I am trying to draw a graph here, it is the zero line. Okay, so compression I will try to draw it to the right side. If it is tension, I will try to draw it to the left side. Now this fiber, okay, I will try to locate here. Do you think this fiber at the top will have the maximum compressive stress? Yes or no? Why? Because it is compressed the highest. Because we have the equation dl is equal to PL by AE, I have actually made this equation like this. So more the deformation induced, more the stress. It will have the highest compressive stress. So I can actually show it with the other color, that would be good. So this would have the highest compressive stress. This would have the highest compressive stress here. The next fiber will have slightly lower compressive stress. Then the next fiber will have slightly less, and it would form. And if you find this, it would be a linear variation here. Okay, this is actually the compressive stress. And the fiber at the center will have what? No stress, because it's neither expanding nor compressing itself. And if you try to again draw this stress in the tensile direction, so let me draw it to the other side. This fiber at the bottom will have the maximum tensile stress, and the next fiber will be like 101.8. So that means it is stressed, it is elongated less. So therefore, the corresponding stress will be less. So it will have slightly less here, slightly less, and it will go like this. This is the variation of the stresses in a component which is subjected to bending. Okay. And now with this concept you can decide why most of the components would actually easily fail in bending than pure compression or pure tension. Suppose if I ask you to break this pen, anybody in the class would try breaking the pen like this? Anybody would try to break the pen like this? Why? Why can't you do that? That would definitely induce stress, no? But if you are trying to do that, then all these fibers are taking the load equally. That means there is unity. I think you have heard your, I think maybe that if you still remember the moral stories, unity is strength or something like that, you heard, no? So everybody is taking the load equally, and therefore everybody participates in taking load, and it is very difficult to apply a load which will go beyond the breaking stress of this material. It is very difficult to break. But if you are trying to break the pen like this, you can break, because there is no unity here. Why there is no unity? Somebody at the top is unnecessarily being stressed a lot. And there are people inside, as you go below, some people at the center are not taking any loads at all. Their presence is of no use. Of course, there is one more use later. You will understand that they are not taking bending stress, but they are taking shear stress. You will understand it later. Okay? But when only considering bending stress, all the fibers at the center are not taking loads, and the fiber next to next are taking only a small amount of load. Only these are taking the maximum amount of load. So therefore, it is very easy for you to induce huge amount of stresses by bending. It is very easy to stress a member in bending, where some fibers will have huge amount of stresses. That stress may go beyond their allowable stress or what the material can take. It is the reason why if a bike falls, do you feel any component would actually crush under compression? It is usually most of the failures are under bending. Your handle bends out of bending. Your pedal would actually bend out of bending. Most of the components would actually break out of bending, and maybe some cast iron components may break due to impact loads, and they may be brittle and they may break. So most of the times the component failures are due to bending. So this is a very important concept for engineers to understand this. Otherwise you may end up in not able to really do justice for engineering design. Okay, so you should understand this concept of bending. So recalling this, what I'm saying is that, so whenever you apply a bending moment could be applied maybe through a point load here, or maybe through a UDL here, or maybe an external moment here. And each of these points, in SFD BMD you draw this SFD BMD, no? The point loads and all that. You draw BMD like this, SFD something like this. Okay, something like this you draw. This is all you're done. So at each point the bending moment is different. Let me draw it here. Okay, guys, if you got a simply supported beam, if you got a point load at the center, can you plot the bending moment diagram? How? Show me. Suppose if this is P, what is the reaction at this side? 0. Guys, this is a simply supported beam. And if this P is exactly at the center, what is the load taken by the right side? I was shocked when somebody said 0. And this is P by 2. Okay, if I want the bending moment diagram, draw a line. Then bending moment about this point. See the forces, no moments, 0. Now as you actually cross here, there is one force going upwards, P by 2, but there is no distance. So it is almost 0. And as you go further, P by 2 multiplied by this distance will increase, and it will keep increasing up to this point. And at this point you will see that it is P by 2 into, suppose if this distance is x. Suppose if the whole distance is x, then it is x by 2. So P by 2 into x by 2. So it is, so suppose if it is Q, so usually it is called as L. Okay. It's called as, okay, then you will see that bending moment will become P by 2 into L by 2, it will become how much? PL by 4. And again it will go the same way in this direction. So this is the bending moment at this point. So that means if you know the bending moment, can you decide whether the metal will fail or not? Cannot be decided by formulas like sigma is equal to P by A, because these are for normal stresses. We need to have a new formula for this. So the formula is this. I am writing here, and it's very easy to remember. I will tell you how. M by I is equal to sigma by Y is equal to E by R. I am going to tell you something now that nobody will forget. Who is the best music director in India right now? Huh? Who? A.R. Rahman. A.R. Rahman was actually tutored by whom? A.R. Rahman. Okay, who is the next person? Who actually taught him? Okay, I think there's one more person who is actually senior to A.R. Rahman. No? Who is that? Huh? Ilayaraja. I think people say A.R. Rahman worked for Ilayaraja earlier. Okay, so Ilayaraja is like some sort of a guru. Okay, can say. Now, suppose if you are a singer, and if you want to go and request for a chance with Ilayaraja, what is the 6 words that you would say? Okay, you are a singer. Okay, he is the music director. His name is Ilayaraja. You are supposed to say 6 words. Okay, requesting you for a chance. Now, what would be the words? I think it will match this. Please think. Yeah. Come on, guys. Yeah, the first 2 is right. And these 2 are again right. You know what is this? Now, what are these 2 here? E and R stands for Ilayaraja. Please fix these 2 words now. Sing for you. Exactly. So, if you know this, you remember this formula. Okay. Okay. May I sing for you, Ilayaraja? So, you take M out of this, you take I out of this. Sigma, this is sigma, this is for Y. You take Y out of this. Sigma for Y, this is E, this is R. So, you get this equation. So, now you may feel this is some random terms related to bending which are actually placed in some order. But if you see here, basically M refers to the amount of bending applied onto this section of beam, or it may be like the moment at this point of the beam, M, the moment at any point of the beam, M. I refers to, maybe in civil engineering, maybe in the first year you had elements of civil engineering, no? You found out moment of inertia, right? I. Do you remember what is the formula for moment of inertia of a rectangle? Can anybody remember? I is equal to BDQ by 12 or something. Okay, so this is actually the moment of inertia for this beam. Suppose if the beam has got a cross section of rectangle, it has got a rectangular cross section. This is B, this is the breadth, this is the depth, then I is given by BDQ by 12. So this is actually derived from using the equation integration of y square dA. This is actually derived from this integration of y square dA, where if you try to integrate all the small areas dA into y distance for all this surface about this neutral axis, you get this formula. Okay, so BDQ by 12, this equation did not land up from anywhere, somewhere. So using this equation, they have derived this. Okay, I is equal to BDQ by 12. And you know here, M is known to you, I is known to you. What is sigma, you know? Sigma is stress. And let me write this as sigma B. So can you understand why I have written sigma B? B stands for bending stress. It is basically due to bending. Okay, and then sigma B for Y, I am saying. Sigma B for Y. That is, here you see that the stresses are different in different locations. So it's not a common stress like sigma is equal to P by A. Sigma is equal to P by A you used earlier, no? Now you add the same stress throughout. When you applied a load like this, you had the same stress throughout every point. But here, the stress is different. Okay, if you want a stress here, then you should mention what is the distance that you want from the neutral axis. this distance you want. Okay. Now if you supply, suppose if this is D, if this is D, depth D. So I said only this is D, sorry. I think I made a mistake earlier. This is the whole, this is depth, this is breadth. So then this becomes how much? D by 2. Okay. If you apply this y as D by 2, then you will get what stress? Maximum stress. If you apply y is equal to 0, then you will get how much? 0 stress, because there is no stress at this point. So the sigma is always related to y, where y is the distance of the fiber, any fiber that you are considering, from the neutral axis. If you substitute y as d by 2, you get the maximum stress. Okay? And then what is E? What is E, man? Young's modulus. Young's modulus is obviously, it is actually stress by strain. Okay? So that is the property of the material. You can use a simple tension test to find out Young's modulus that you have done in the first lab. And then R refers to radius of curvature. So that means if this part of the beam, when you zoom it out, guys, if this part of the beam, when you zoom it out, suppose if it looks like this, then from any perpendiculars that you draw here, if this perpendicular goes and joins some point here, the distance, this radius of this distance is called as the radius of curvature. I'll not be able to show because it's going out of the board here. Okay, that is called the radius of curvature. More and more bending moment you apply, the curvature becomes less. So that means when you have got a straight beam, the curvature is infinite. So what is actually curvature? So curvature is, if you draw perpendiculars like this, it goes and meets here, no? That is actually the radius of curvature. Suppose if it is infinity, these lines will meet it. Suppose if it's a line, this perpendiculars will meet at infinity. So what happens to the curvature? R, infinity. So when the beam is straight, it will be infinity, but when you start to bend, it will have some values, and with the increase in moment, this radius of curvature starts to decrease. It is the reason it is on the other side of the equation. It is at the bottom side of the equation. Okay, so here, let me again make this equation clear. It is May I Sing For You Ilayaraja, where M is the bending moment. What is the unit for M? What is the unit for M? What is the unit of M, bending moment? What is bending moment basically? Force into distance. So you can call this as, you can replace this with Newton meter or Newton millimeter. It's left to you. Okay? This is bending moment. And what is actually the unit of I? M to the power of, here I said I is equal to BD cube by 12. You said I is equal to BD cube by 12. So here B is meters, D is meters, meter into meter to the power of 3, it becomes meter to the power of 4. And here, what is the unit of stress? What is stress? Load by area. So Newton per meter square, load by area. Load divided by area. And what is Y? What is Y here? Y is any distance from the neutral fiber for which you want the stress. If you want the stress at this point, you should substitute Y as equal to this. If you want the stress at the extreme fiber, you should substitute it as D by 2. Okay. So what is the unit of Y? Y is just a distance. What is Y? M. And what is the unit of Young's modulus? Young's modulus is stress by strain. Strain has no units. So Young's modulus and stress has the same units. So it is Newton per meter square. And what is the unit of R? Radius of curvature. Radius of curvature is again distance. because it is the length. Okay, so it is meter. Okay, now if you see this units are consistent. Units are consistent. This meter, it goes off. You can bring this here, it becomes meter cube. You can bring this here, it becomes meter cube. Okay, so all of this have the same units. In this way, you can confirm that the equation may be right. It's not a confirm, and we will need some time. Maybe in the next class, we will try to derive this equation for bending moment. This is a very useful equation to actually create interest on this equation. I will try to solve a very simple numerical, most simple numerical. Guys, assume that you are a owner of a resort, okay, and you have a swimming pool, and you're buying a diving board, which is attached at some point here, or maybe extended to some point. This is a diving board. It is a diving board, and this diving board has a length of around 2 meters. Okay, diving board is made up of what? Is it made up of steel? Guys, diving boards are made up of steel or aluminum or what? Marble. Yeah, what is it? Yeah, sometimes wood. Okay, guys, okay, I think wood is a better material, and you can have even maybe glass fiber reinforced plastics or plastics. Okay, it should not be brittle, because the person may actually end up suddenly crashing down. Okay, guys, so definitely it's not actually metals, because it's too heavy and it will not flex easily. It should have something to flex easily. And imagine that there is a plastic or wood or something, and that metal, suppose if I take a piece of that and actually do a tensile testing on that specimen, like this, guys, it looks like this. Now the tensile test specimens are like this. Both sides are to hold like this and apply load. They found out that the maximum stress this can take is actually equal to 10 Newton per mm square. So that means 1 kg per mm square. So that means they actually took out a sample out of this. They sent it to some lab. They said that it is going to fail at 10 Newton per mm square. Okay, it is a failure stress. Now they are saying that this length of this is 2 meters. The width of this is around 0.5 meter. And this height is, now what do you think is the height, guys? 10 mm. 10 mm is 1 centimeter, very thin. 30 mm, yeah. Maybe you take even 5 centimeter, that would be okay. 50 mm. Okay, take quite thick. I don't want somebody to 50 mm. 50 mm in terms of meters is how much, man? Okay, everything I express in meters, let me express this in meters. 50 mm is equal to how much? Is it 0.5 meters? 0.5 meters is 500 mm. So 0.05 meter. So everything I specified here. Guys, I just wanted to show you how this equation could be used. I said, may I sing for you, Rajana? Basically, in this equation, the first part of the equation is very much used in most of the problems. Guys, hello. This first part of the equation involving these first 4 terms are very useful in trying to find out the unknowns in most of the numericals. So in this case, what I'm supposed to find as the owner of a resort is what is the maximum weight of a person that this can bear. Any guess? Any guess? Okay. Imagine that you are running a very high profile people, you are handling high profile people, like you are actually, maybe this resort is booked for Ambani's son's wedding. And all the top people, no, I'm trying to make you serious about the situation. Okay. And you don't want anything to happen. And you want to recheck on this. What is the maximum weight? Any guess? Okay. Now forget about this value. Suppose if it is made up of plastic, what is the maximum weight it can take? Now the length is 2 meters. A person goes and stands and jumps, and forget about jumping. Even if he stands, it should not break. So 200 kgs. Okay, he says, your friend says this weight of the person can be 200 kgs, which is approximately 2000 newtons. 1 kg is 9.81 newtons, multiplying it by gravity. So you know force is equal to m into a, mass into acceleration due to gravity, you get it as force here. So that is 2000 newtons is the force. Now guys, everybody knows by common sense, if this is going to break, how many will agree that because of the weight, this board is going to fail at this point? Please raise your hands. Okay, anybody feels that board is going to fail at this point? Okay, how many feel that it will fail at this point? At this point? Please raise your hands. You feel so? How many feel that it will fail at this point? Okay, now failing at this point, failing at this point, failing at this point. Which has the highest chance of failure? A, B, C? A. That's by common sense, because you have drawn this, you have solved a numerical like this in SFD BMD. Okay? In SFD we have actually, like in B, suppose if it is a point load on a cantilever beam, if this length is L, if I am trying to draw only bending moment diagram, then if I see moment at this point, no force is on to the right side. So no force, no distance, it is 0. But if I keep moving like this, then there is load into distance. If I keep moving, at this point you get the highest force into distance. So it will be definitely a linear relationship like this, and you will have the maximum bending moment, which is actually equal to P into F. So you will have M max, which is actually PL in this case. So that means this value is the maximum bending moment induced in this beam, which I need to substitute in this equation here. Okay. Now can you tell me if this load is how much as per this person? 2000 newtons. If this length is 2 meters, what is M? What is Mn? 2000 newtons multiplied by 2 meters. How much is it? 4000 Newton meter is the bending moment that I need to substitute here. Let me substitute here. So I substituted the first part of the equation. So that is 4000 Newton meter. 4000 Newton meter. What is that I should substitute here? Hello? BD cube by 12. So can you tell me what is B? What is B in this equation? 0.5, because you are referring to this part, it is a section of the beam. You are referring to this part of the section of the beam. So here, this is the breadth. So I is equal to, I'll find out here, I is equal to BDQ by 12. So B is how much? 0.5 meters into, so much is D? How much is D? 0.05 meter cube divided by 12. If somebody can use a calculator and tell me what is the value that you got, that would be a great help. 0.05 to the power of 3. So much is this? 5.2 into 10 to the power of minus 6. Okay, 5.2 into 10 to the power of minus 6, which I am substituting it here. Okay, and then sigma B. Guys, what is that I should substitute here? Sigma B, can you tell me? I took a sample out of this. I took a sample out of this diving board and sent it to lab. Now what did they say? The maximum stress it can take, sigma B is 10 Newton per mm square. So this is mm square. So you should convert this into meters, because everything is in meters here, it would be wrong now. So what you would do, 1 mm is actually 10 to the power of minus 3 meters square. It will become how much now? It will become 10 to the power of 6. 10 to the power of 6 Newton per meter square now. If it comes this, if you bring this 10 to the power of minus 3 upward at the top, okay, then it would become 10 to the power of 10 into 10 to the power of 6. So for 1 mm square it is 10 newtons, for meter square it is 10 into 10 to the power of 6 Newton per meter square. Guys, can you tell me why? What is why? What is why? Why is the distance from the neutral fiber? Neutral fiber is here. Neutral fiber is here. If I am trying to zoom this off, if I am trying to zoom this like this, hello? Idina zoom madidre ee tara kanutte. It is a diving board. It is a diving board. From this, the neutral fibers will start. Okay, it is the axis of the neutral fiber. So here, y refers to the distance of the neutral, distance of the extreme fiber from the neutral axis. So how much is this distance? 0.05 divided by 2. Okay, so y is equal to 0.05 divided by 2. Guys, I made a mistake here. Can you tell me? I was supposed to find what is the maximum weight of the person. Now the maximum weight of the person, I should have actually put this as P newtons. I should actually put this as P newtons. Here it could be like 2P Newton meter. Okay, so instead of actually trying to write this exactly, okay, I had already given the weight of the person. It was wrong because I was supposed to find the weight here. Okay, I said it is actually 200 kgs, but I was supposed to find the weight. Instead of 200 kgs here, which became 2000 newtons, I am writing it as P newtons. So it is actually P newtons into 2 meters, it become actually 2P Newton meters. I am substituting it here because I am supposed to find P. So 2P Newton meter, it's actually 2P Newton meter. Now, it's just easy for us to solve this equation and find out P. And your friend said the maximum weight that this can bear is around 200 kg, which is 2000 newtons. Now you will find out. Please find out. Please find out. So P is equal to. So P is equal to, P can be taken this side. So this divided by 2. So 10 into 10 to the power of 6 Newton per m square. Here you can see 5.2 into 10 to the power of minus 6 meter to the power of 4. Here you can see 10 to the power of plus 6 and 10 to the power of minus 6 cancels out. And then it is 0.05 divided by 2. It is 0.025. And again this 2 comes here. Now this 2 comes here onto this side. So what is the answer? Huh? 10? 10? 1040? Guys, anybody confirming this? You got 1040. It's better I show the class because it will be a record. It is a class which I am handling, and these people are not even interested in using a calculator. It will be explored. Okay, so 1040 newtons is what weight? 104 kg approximately. Guys, I just found out that the maximum weight that this can bear is 104 kgs. Imagine one of the celebrity who is like 125 kgs comes and stands on this. So as an engineer, you're not supposed to wait for it to break. Suppose if you had already tested this, if you had sent it to lab and you got this value properly, then you will definitely get what is the maximum weight it can bear. This is a very, very useful equation. What you just used was a very useful equation trying to find out what is the maximum load it can take on a swimming pool diving board. Given the maximum stress, why I actually took 10 Newton per mm square is like that is a tensile stress of wood. So I took it as 10 Newton per mm square. Suppose if it was steel, then I would have taken it as how much? 250 Newton per mm square. Higher strength steel, 500 Newton per mm square. I only took 10 Newton per mm square because it was wood or plastic. Plastic could be even less, like 5 Newton per mm square. Okay, so this is a very, very useful equation. So please, this chapter I'll try to finish in the next 5 classes. So please be attentive. So this is the first practical example of this use of bending equation. You only used the first part of the equation. Most of the times you end up using the first part of the equation. The next part of the equation is only used for finding out the radius of curvature. Okay.